Good evening, everyone. I am Ch.Jithender Sai and our team G615 and our mentor Dr. A. Shilpa Gupta and our team members J. Meghana, T. Anjali, M. Chinmay and P. Surya Teja and our group project title as named GNN-AID. GNN stands for Graph Neural Network and AID stands for Analysis, Interpretation and Defense. And giving you a brief about GNN, what is GNN-AID? GNN-AID is an open source framework that unifies interpretation, attack, and defense methods of a graph neural network, enabling robust and trustworthiness analysis through a user-friendly interface. To begin with, let's understand what is GNN-AID. GNN-AID is a unified open source framework designed to make GNNs trustworthy, interpretability, and robust. And GNN-AID integrates three key modules: analysis and interpretation, attack simulations, and defense mechanism. GNN-AID is built on Python geometric supporting major GNN models. GNN models means graph neural network models: GCN, GAT, GIN, GraphSAGE, Graph Transformer, and KA-GNN. And it provides explanation methods, attack types, and defense strategies in a no-code interactive web interface. Enables systematic evaluation, visual reasoning, and comparative analysis on datasets like Cora, Citaser, PubMed, and OGB. And OGB is the biggest dataset in which we can train our GNN models. This is a system architecture of GNN-AID, a framework designed to make graph neural network more trustworthy, interpretability, and secure. It is divided into three main tiers: the presentation tier, the application tier, and the data tier, each with a distinct role in the end workflow. The presentation tier. The presentation tier is built using React. Here, user can select a preloaded dataset or upload a custom dataset for analysis. They can define metrics and send the configuration to the backend of the model's execution. Once the analysis is complete, user can view a result and visualization directly on the interface, assuring a smooth interactive experience. And then when we move on to the application tier is a core processing layer developed with the Python geometric and fast API. It houses two major components: the models module and the attack defense module. The models module supports multiple GNN architecture like GCN, GIN, GraphSAGE, GAT, KA-GNN, and Graph Transformer. Each model can be trained and evaluated for the performance. The attack and defense module ensures the model robustness. It simulates Bayesian, aviation, and privacy attacks and applies respective defenses. Afterward, the pipeline performs model training and evaluation, integration, defense, and measuring the secure accuracy. All proceed outputs are sent for visualization and the data storage. And when we move on to the data tier the data tier used MongoDB to manage all datasets, model checkpoints, and evaluation metrics. It ensures experiments are stored, reproducible, and easy to compare. The interpretability and visualization manager works here to generate interpretability graphs and visual results, helping users understand model behavior and prediction logic. To sum up, the presentation tier handles user interaction, the application tier runs model running, attacks and defenses, the data tier stores the results and visualization. Together, these layers make GNN-AID a complete, modular and secular framework for analyzing and defending graph neural network. This slide shows the technology stack and tools timeline used in our project. It highlights how technology used evolved over time and why these specific tools for the backbone of the system. Let's quickly go through the stack for the base programming language to the modern framework that the power of the entire architecture. Release and ecosystem. It all begins with a Python, a versatile and powerful programming language. Python's simplicity, a huge ecosystem, made it perfect for building machine learning and backend system, which is why it's essential to our project. HTML, CSS, and JavaScript. Next, we have HTML and CSS, which become the standard of web development. They define a front-end structure and design, On the top of that, JavaScript emerged as a large language of the web. It adds interactivity and forms the foundation for framework like React with, with the use of a presentation type. NumPys and Pandas. Why NumPys Pandas gained efficient numeric computation? They gave Pandas a powerful data analysis library for simplifies the data handling and pre-processing, an essential part of our ML pipeline. React and Tailwind CSS. React, developed by Facebook, is an open source front-end framework used in a project for building an interactive user interface. To style React components efficient, we use Tailwind CSS, a utility first CSS framework that makes a UI fast, modern, and responsive. MongoDB and PyTorch. MongoDB, a non-SQL database, was introduced to handle unstructured data efficiently. We used to store datasets, model, checkpoints, and evaluation metrics. Then PyTorch emerged in a deep learning framework, powers our GNN models and enabling flexible experimentation with neural architects, fast API and UVCon to connect front end and back end efficiently. We use fast API modern a web framework for Python needs speed and asynchronous support. It runs a UVCon as ASGI server that serves a smooth and scalable API communication, perfect for the real-time model evaluation and visualization. Sorry. Redux UI. Finally, Redux UI supports efficient rate management in the front end, ensuring seamless interaction between user action, dataset, and model outputs. Conclusion. So overall, all the timeline shows the evolution of the tech stack. For foundation tools like Python, HTML, and JavaScript to advanced frameworks like React, FastAPI, PyTorch, and MongoDB. Together, these technologies from the modern, scalable, and high-performance ecosystem that powers the entire GNN-AID framework. This slide explains the mathematical foundation behind our framework. It includes the core formulas used in the model interpretation, adversarial attack generation, defense mechanism, and robust training. We'll briefly go through each concept, starting from GraphMask, then moving to the FSGM, PGD, and finally regularization and adversarial training objectives. GraphMask. The first evaluation represents GraphMask, which helps interpret graph neural network. Yes, the final message, MUKV, is passed from one node to another. The gating factor Z, KUKV, decides how much of the learned message to keep, while the remaining part behinds with a bias term B power K. This mechanism helps highlight important node connections while preventing overfitting and ensuring stable message passing. And then fast gradient sign method. FSGM. The fast gradient sign method or FSGM is used to create adversarial examples. It adds a small and controlled perturbation sigma in the direction of the gradient sign to the original input x. This slightly changes the data to flow the model, helps us evaluate how sensitive or robust the model is against such attacks. Projected gradient descent (PGD). Next, it is a PGD, projected gradient descent method, which extends FGSM. Instead of a single update, PGD iteratively refines the adversarial example by repeatedly adjusting the input in the direction of the gradient. Each step ensures the change stays within a small limit known as the epsilon boundary, so the perturbation remains realistic while maximizing the attack effects. Gradient regularization. The formula introduces gradient regularization, which adds a penalty term to the loss formula. It ensures the small input change doesn't cause large output changes. The parameter lambda controls how strongly this regularization is applied, while z is a slightly permeated version of x. This helps us in smoothing the model's prediction and improving stability. Adversarial training. Finally, adversarial training combines both normal and adversarial losses. Here the total loss function L includes the original data loss plus and adversarial loss, scaled by the factor lambda. By training the model on the both clean and attacked samples, we significantly improve its robustness and generalization ability against adversarial perturbations. Conclusion: to summarize this equation from the core mathematical frameworks of a model, GraphMask enhance interpretability, FGSM and PGD generates advisable examples, and regularization and adversarial training strengthens the model defense. Together, they ensure a system not only performs well but also remains robust, explainable, and secure. And this is how GraphMask, fast gradient, projected gradient descent, gradient regularization, adversarial training helps in the mathematical formulation of GNN-AID. This slide explains the key model parameters used in graph neural networks and their significance in shaping model performance. Each parameter has a specific purpose for controlling how features are transformed to ensure the model generalizes well without overfitting. Weight matrix. The weight matrix represents the learnable parameters at each layer. It determines how features from different nodes are combined and transformed in simple terms. It controls the feature transformation process and directly influences how the model learns representation from the graph. Activation function. The activation function introduces nonlinearity into the model. Without it, networks and would behave like a simple linear function. It improves the model explanation, allows to capture complex relationships between the nodes and edges. Loss function. The loss function measures the difference between the predicted and actual values in the core objective and guides the entire training process. Minimizing the loss helps the model improves accuracy and reduces prediction error. Learning rate. The learning rate defines the step size during optimization. If it's too high, the model may not cover it. If it's too low, it's may too long to train. So it's crucial to maintaining a balance between the coverage speed and stability. Number of layers. The number of layers determines the depth of the graph neural network. More layers allows the model to capture broader neighborhood information, but too many causes can cause oversmoothing. So it's about finding the right depth of the repetitive field. Optimization. The optimization algorithm minimizes the total loss function by updating parameters efficiently. Methods like ADAM and SGD helps achieve faster and more stable configurations during training. Attention confidence. The attention confidence are used to Attention used to GNNs like G80. The assign weights to neighbor nodes helping the model focus on the most important relationships, which improves interpretability, learning, and quality. Dropout rate. Finally, the dropout rate at the regularization factor that randomly drops neurons during the training. This prevents the model for memorization patterns and reduces overfitting, improving generalization on unseen data. The weight matrix and activation function shape the learning structure. The loss function, learning rate, and optimization control training behavior. Number of layers, attentions, dropout, affect overall the model generalizations. This slide shows the key improvement we made over the original GNN-AID paper. While the original version was just a Python library, we rebuilt it a complete interactive web application that's easier to use and visual more informative. Main improvements. We introduced a non-code interface for selecting datasets, models, attacks, defense, and explainers, making it accessible to non-programmers. We added real-time visualization using WebSockets to track training accuracy and loss, attack success rate, and robust accuracy during defenses. We also built a model experiments tracks, storing every run with a unique ID for reproducibility. And finally, we enhanced user accessibility so even beginners or researchers without cooking skills can use the system easily. Challenges and learning. Some challenges we face, including framework integration, dataset mismatch, and handling large graphs, which we fix through asynchronous design, dynamic pre-processing, and progressive rendering. We also observed the GNNs are highly sensitive to small penetration and the combined defense can sometimes low accuracy, but visualization really helped in explaining this behavior. Potential improvement. Going forward, we plan to add a confidential explainer supports dynamic graphs and even use a reinforcement learning for automatic hyperparameter tuning. Overall, these improvements make GNN-AID more partial, scalable, and explainable on the original paper. Thank you.